Thanks for the nice introduction, and thanks everyone to being here to listen to my talk. And it's a great honor to receive this award and to have the chance to present the work from our lab. I give this lecture on behalf of Professor Dr. Davide Squarmza. Davide is the director of the Robotics and Perception Group in University of Zurich. I did my PhD in his group from 2016 to 2021. So a lot of the work has happened after I finished my PhD. So I will try my best to explain it. And actually, the work started with the paper we received the Frontier of Science Award, SVO. So at first, I will give you a brief introduction of what is a vision-based autonomous drones, or in general, vision-based autonomous robots looks like. So in order for a robot to execute like a useful task in real world, for example, here the robot want to reach a goal indicated by the star, but it needs to avoid these kind of obstacles. So in general, you have this somehow simplified paradigm that the robot have this onboard sensing, like it has images and also the inertial memory unit sensing how the robot moves in the space. Then you have vision algorithms, or in general perception algorithms, to estimate the states of the robot and the information about the world. Then you have planning and control module that does decision making and low-level control, generate control signals, sending to the robot. Then the robot execute in the real world. Then after a small time, after it is executing in the real world, its environment and its position will change, so it will receive like a new sensor data. Then its loops continues. So it's kind of a simplified illustration of how autonomous robots or drones works in real world. So what do we mean here by robot states here? So in general, a robot states, most important robot states consist of its position, where it is, orientation, and velocity. It basically answers the question, where am I for the robot? And it also contains the world information, like a 3D local map of the environment. It tells the robot what is around me. So with these two information, the robot can make like smart planning and control decisions to achieve this task. So as you see, it's kind of very systematic work to integrate the robotic platform. So for these vision algorithms, we have computer vision that is developed for a long time. So what is actually the challenges for robot vision is that the vision algorithms or perception algorithms for robots needs to be executed in a closed loop fashion. So it has to be very efficient. Then it has to be robust to real world situations. For example, if you have the camera, when the robot moves very fast, you have motion blur or some kind of effect that will greatly damage the performance of the vision algorithms. Also, since the vision algorithms is integrated in the large system, one has also to care about the synergy between the planning and control and also the sensor configurations. So it's kind of more complicated than the standalone vision algorithms, but it also opens very many research questions. So in Davide's lab, the main focus is about to use cameras as the main sensor. Why do we use cameras? Because cameras kind of, with the development from the industry like mobile phone or something, cameras are very cheap and it's also very lightweighted. And also the camera with the image, we often say image is worth 1,000 words, right? So with the image, it is also contains a lot of information. So it provides actually a lot of information for the robot to make very good decisions. So this brings like the work that we won this Frontier of Science award. It is called SVO. It is highly efficient and versatile visual odometry. So it solves a single problem in the previous diagrams. It basically tries to estimate the motion of the camera from the images. As you can see from the video, the lab mat actually shakes the camera and moves the cameras around. So here you can see that the motion of the camera is estimated in real time. And it also kind of very robust to the camera shaking. And also, as I said, it has to be very efficient. So in this case, it runs on a very simple laptop, like 6 or 7 years laptop. It only takes like several milliseconds to process. Then it also can estimate the camera trajectory very robustly. So SVO, it basically estimates the camera motion just in one sentence. So with this pipeline in place, what can we do we can do some tasks. It's kind of the state of the art 6 or 7 years ago. Like we can deploy the odometry on board and do autonomous navigation. So in this case, the people throw the quadrotor in the air. Then it runs SVO on board, so it tracks this kind of green feature points, so it can stabilize the drone. And also here, if you have the estimation of the pose of the drone, you can command it to achieve some other tasks. Here, like it is kind of a flying scanner. If you fly around this area, then you can build a nice model of this thing. This thing can be useful in the search and rescue scenario, and other also digital twin stuff in the augmented reality or virtual reality industry. So this is kind of 6 or 7 years ago. So what has the advance of past few years of research brings us? So I want to show a result like 1 or 2 years ago from David's lab. So first, let's look at the video. So now with the onboard sensing, we can actually command the drone with only onboard computing and data that fly through this gate with very high agility. So it's like at the beginning of my PhD, it's not. It seems to me like not possible. So it's like really very big advance in the field. It is enabled by several technologies I will introduce in the talk. So basically, the idea here is to compete against the world champions in this kind of racing through the gates. So it turns out if you build your system really carefully and use very advanced algorithms, you can beat the world champion in this kind of competition. Okay. Before I go into the details of the drone racing, because drone racing we do not actually have a chance to watch the event a lot, but actually the advance in perception and decision-making algorithms has actually made a very big difference in our life. So this is kind of a robot vacuum cleaner. Now we have many people has like autonomous vacuum cleaners in their home. Like before like 2018, this is kind of a time lapse of the trajectory of the Roomba cleaner. So it's kind of just walk randomly, bumping into obstacles. So it takes like 20 minutes to clean up this 20 square-ish room. But after 2018, so they put a camera on Roomba, and also they equipped the Roomba with SLAM algorithms and also obstacle avoidance. Basically, a full stack of robotic algorithms on board, so it can complete this kind of task very efficiently. Not like 5 minutes also, but it's still far from human. And also for humanoid robot, I believe like humanoid robots is like the hot topic in the market now. I guess everyone has seen this kind of Boston Dynamic demonstrations. So on the line, it also uses onboard sensors to estimate the position of these steps, and also planning its trajectory, like in terms of humanoids, like the gates before. So it's like the same thing as at the drone racing. You perceive the environment and you plan your motion ahead, then you execute. And also it happens not on Earth. Like on Mars, you also have this SLAM on board. So this is kind of the NASA Ingenuity. Like it's the first helicopter on Mars. It actually completes like 72 flights on Mars. And finally it crashes, but it's already a very good achievement. So for the application of the extraterrestrial exploration, it's actually important to make the robots autonomous, because on Earth we can say, okay, even if the algorithm is not working, we can teleoperate. The latency is acceptable. But for operation on Mars, it's like if I remember correctly, the runtime is like up to 20 minutes. So it's not possible to have this teleoperation there. So actually, in history, the first SLAM algorithms or visual odometry algorithms is basically inspired by the need of the autonomous operation on Mars. Now it's also very great to see that now we can have drones flying on Mars. And also for precision culture, I think it's also one big application of drones, autonomous robots. I think it is a startup that is spinned off from David's lab that is in South India. We can see that the drones can fly, build a map around the world, can fly in the thing, also avoid collision. It can also spray like pesticides in the field, which is harmful for human. So from the previous example, I hope I can convince you that computer vision and the decision-making algorithms is making mobile robots autonomous, but humans are still preferred in most applications. For example, now we do not see many robots around. I mean, China, I guess we see some more. Like in the hotel I'm living in, I see like the robots sending like deliveries to the room. It's working somehow, but it is still far from. Why do we not have like robots that can do housework for us? So the thing that current robots are still far from human performance in several aspects, like agility, facility, and robustness. So basically, a failure in the robotic system will be very very catastrophic for commercial products. So in order to have very good commercial products, you have to be very high in all these standards. So in David's lab, that we do not focus on all kinds of robots. Instead, we focus on drones. Why do we focus on drones? Because drones are kind of a very difficult robot. Because if you think about a wheeled robot or legged robot, if your algorithm fails, you can just stand still. You can have a good chance to recover. But if you have algorithms running on the drones, if the algorithm fails, the drone will crash. So it's a comparatively difficult problem. And in the lab, it's always thought of that if you can solve problems for drones, it is a proxy to solve really fundamental research questions that can be hopefully be extended to other platforms. So in terms of drones, one of the things that can we beat human in flying the drones. So it's always it's like AlphaGo or other AI algorithms that we always try to match human level performance. So it's always so this kind of human level drone race performance, I think, has been a recurring topic in David's lab for the past 5 or 6 years. And as I showed in the first video, it actually has some great achievements. So apart from a purely scientific pursuit, so what can we get from the drone being agile? Actually, for drone being agile, it also has these practical meanings. So for people familiar with the drones, like the battery of the drone does not last very long. At the beginning of PhD, I think the battery for a drone in the lab only lasts like 5 or 6 minutes. So it's always very tricky to do experiments. You need to have a backup batteries that is charging all the time. But now, like if you have this very big drones or commercial drones, now the battery is like 20 minutes, but it's still not very long compared to ground robots. So by flying fast, drone can be more productive. But it is not always the case. So as shown in this figure, I think it's a paper from David's lab, that if you have, of course, if you have a faster flight speed, you can cover more range per battery. But if you're flying faster, then due to air drag or other unmodeled effects, the actually operation range can reduce. So if we look at this graph, what is this commercial drones lying around? So for commercial drones like Skydio or DJI, which are top drone manufacturers, they are lying basically around this kind of area. I think it is mainly for safety issues, like the algorithm there is not robust enough to operate at higher speed. But it's finally a goal that we can have more agile drones that can help us do more things. And for drone racing, they don't care about safety that much. So they care about minimize the lifetime. So it's kind of at the other end of the spectrum. But anyway, for the application of drones, it's important to consider our battery or productivity to have it be more agile that can operate at high speed. So for drone applications, actually drones has a lot of applications. Like at the beginning, I think people think about doing drones for search and rescue. If you have a like earthquake or something, you don't have ground robots that can go through this area. So you can have drones hovering around and inspect the rings. And also we have exploration and inspection of this industry industry application, like in power plant or something. And also we can have monitoring, and also I think some companies started building like autonomous cars. They started building autonomous drones for delivering people. I think I guess it's still very far away, considering safety. And also, as I mentioned, for fast exploration on Mars, that drone is also useful. So let's back to so that's all the background. Like why do we want drones? Why do we want agile drones? So that actually there's a history. There's quite some history of agile flight for drones. I think almost 20 years. So let's look at the related works on agile flight. So here we categorize the work on two axes. Basically, the horizontal axis is agility of the drone. The vertical axis is whether the drone relies on external sensors. Yes, at the beginning of the drone research, because of the limits of the computer vision algorithms, the drones has to rely on external sensors like the GPS or motion capture system to work reliably. So back in 2006, I think Andrew Ng, who is a big name in machine learning, and with his PhD student at that time, Peter Bill, that actually built this very agile helicopter. I don't know whether you can see this. Like this helicopter is kind of flying backwards, like upside down. So it's very amazing at that time. But this is done like using GPS and also kind of array of external sensors observing the state of the helicopter. And also later, like Rafael Andreu from ETH and also Vijay Kumar from Pennsylvania, that they also said that, okay, since the agile flight is so difficult, what if we can just assume we have perfect perception localization and just focus on the control algorithm, see how far we can push forward. So they did a lot of amazing work in mock-up system. Like this is a historical video, like two drones is playing ping pong, like these small white balls, but everything is captured by the mock-up. Basically, it has like an oracle tells that how the drone moves and how the ball moves. So as a research progress, like after 2012 or 14 or something, that more and more, like also with the advance of embedded computer, that there are more computation you can pack into the drone. So there are a lot of work that tries to deploy more advanced algorithms. SVU is just one example on drones. So now they can do these maneuvers just based on the onboard sensors, like this flying through narrow gap, and also flying through this very cluttered environment. I guess it's from HKUST, Zhao Jishen's group. And but if you compare this, when we use onboard sensors, it's basically like it's not as agile as the thing that we use in mock-up systems. So it indicates that we actually have some gap in the performance that onboard sensor can achieve between the performance that the onboard sensor can achieve and the external sensors. So human pilot can somehow, if you want to categorize it, it's somehow here. So you can see that there's a lot of research need to be done to reach really human level performance. Okay, that's the kind of the history of agile flight. So the real key limit, say, is really the onboard perception decision making. So before I go into details, let's have a look at how this vision-based navigation works. Like this is also like 6 or 7 years ago. As we see before, like the robot tracks the feature on the carpet. That's with these green boards, and then it estimates its motion based on these feature points, and then builds a map, like a local 3D map, based on these feature tracks. Then it has information about its motion. Then it has the information about how the environment look like. Then it can like navigate and do some useful stuff. All this is very nice if you fly in the robot in a very relatively low speed like this. It's always hovering, and you have an image always downwards. You always have texture there, and you don't have motion blur, so everything will work. But if you fly at high speed, actually a lot of stuff will break. So so now I've explained what is kind of the difficulties for vision-based agile navigation. Why when we increase the speed of drones, all the assumptions will break and make the system harder. So the drone is kind of a very special robot. So as I said, it has to perceive all the time to be able to stabilize in the world. And also, if you know a little bit about the control, like the drone is kind of under actuated system. So the drone is hovering; it cannot just horizontally move to the side because it only has a thrust along this direction. So if you want to go to the goal here, it has first to rotate its body frame, like adjust the thrust of the rotors, and let its collective thrust point to the goal. Then it can move to the direction. The thing that it has very challenging for the perception part. Suppose you have this, you rely on some features on the ground to localize and stabilize. When you move this, you optimize your direction or progress to the goal, but actually you can lose track of your perception. So it can actually cause the drone to crash. So it's kind of very common failure mode for drones if you really fly very fast. And also for drones, if you fly with a very high agility, you will always have this kind of very good motion, very agile motion. That the images captured by the camera is very different. If you know like the normal image classification or detection network, you usually don't see images like that. So basically, if you directly use the detector off-the-shelf detect here, it will basically fail. But there are some people. There are also people like working on design like image detectors classifier for drones. And also, as I said, if you move very fast, you will have this kind of unmodeled effect like motion blur. Also, if you fly very fast, you can have very drastic change of the light. So you will have overexposed or underexposed images. And also another very tricky thing is aerodynamics. If you fly very slowly, aerodynamics does not matter. And if you fly very fast, like the turbulence between the rotors will interfere with each other. And also, if the drone descends to the ground, actually the airflow created by the propeller will cause some disturbance to the drone itself. So it's kind of very difficult to analyze this kind of thing. If you want to analyze it very properly, you need to do computational fluid dynamics, which is very expensive. So it's kind of the thing that we need to tackle when you fly with very high speed. There's also latency. So in drone racing, like FPV drone racing, like people have these goggles, and they usually stream the image like 120 hertz per 120 hertz. So you have several milliseconds between each frame. But actually, you still have this kind of blind time between the frame. As I said, I said it, again, it's like if you fly slowly, it doesn't matter. But if you fly fast, actually the small blind time can make a difference. Also, when you for people working with hardware, it's always kind of hardware is difficult to work with. Like a drone, as they say, we can in most papers we can model it as a rigid body, but actually the rotor rotates, so we always have this kind of plastic dampers in this rotor to avoid this. Otherwise the camera will oscillate a lot. You cannot see much. And when you fly fast, actually the drone is kind of soft body, deformable body, so it's kind of a very difficult model as well. With these difficulties in mind, let's look at this perception, planning, and control loop. It's basically a rephrase of the first diagram I made. You have the images and an MU, you have a state animation, local 3D map, you do planning, you do control. This is basically how the robotics is done, like for the past 40 years. It's good because it defines like very clear interface between these modules, and people can work on different parts. And also, when you have an interface between different modules, you have better generalization. So that's kind of the thing that is missing in current data-driven method. But also, it's very fragile. By fragile, I mean, let's say we want to estimate the motion of the camera. You need to have feature tracks. You need to have enough feature tracks. But if you fail, if you have like a textureless area, the information passing from here to here will be completely lost. So it's kind of so to put it in this way, like 3D information opposed or the 3D local map is often too strong a promise. So, but if you define like this, like planning algorithms, we only care about, okay, we just use 3D algorithms. So it's usually there's a tension between these two modules. So if you are familiar with recent advance in robotics, you must be familiar with this vision language action model or end model. Basically, to put it simply, it tries to directly map the action from the raw sensor data. So it basically breaks the interface of different models. And some people say it is kind of also reduce the information loss when you pass everything through a network, but it is up for discussion, I think. Anyway, people has done like amazing work with this kind of paradigm, but the key issue with this architecture is kind of very inefficient to train. So with the traditional algorithms, if you design your algorithms with proper assumption, it basically transfer zero shot to real world, because as long as the 3D information is available, it will work. But for training neural networks, you need a lot of training data. And for drones, it's even worse, because you cannot easily collect many data on drones, because especially if you're doing agile flight. If you're doing agile flight, then you collect data. If your algorithm is not good enough, it will crash. It will create a lot of cost and also very dangerous. And also there's a problem of this interpretability. You do not know like what the network computers in the middle, but also there are some work that tries to have some intermediate results from here. So people are working on this. So, so I think one of the gist from David's work to make this champion level drone racing possible is try to combine like model-based methods, like traditional wisdom, with this neural network. So by using neural network, when you really need to answer these kind of questions, should we train it with or without supervision? Like should we do it with reinforcement learning, or just have some imitation of this expert trajectory? And also, data is the key for the AI algorithms. And also, how can we get enough data? Like I said, getting like training data for drones is very difficult. So like the second question, partial answer to the second question is that yes, we need a simulation. We can collect a lot of data in simulation. That helps a lot. Then if you decide to use data in simulation, there's a problem that how do we address the simulation to reality gap? So now even with the like very powerful render engines, the images rendered from the render engine is still very different from the one you captured from the real sensor. So it's kind of one of the simulation to reality gap that usually hurdles the learning algorithms. So I think this kind of questions are kind of answered through this kind of 3 tasks when pursued the final goal of drone racing. I will first introduce this kind of tool. I think in my view, I don't know what David thinks. In my view, this line is like the foundation for the following success for the autonomous drone racing. So there are basically three tasks that in the past few years the work from David's lab has very successfully addressed. The first is autonomous drone acrobatics. So it's like if you can command the drone relying on onboard sensing only to do this very fast and aggressive maneuver like a barrel roll. And also the second one is to how do you navigate in the wild? Like if you only rely on the depth image from the drone, how can you let the drone navigate in the real world autonomously without collision? So I will first talk about this too. Okay, this is kind of the platform they used for the experiments. I think it has gone through a lot of evolution. I think this drone is actually built with the help of the professional FPV drone racer, like I think it's 15-year-old kids in Switzerland called Marvin. And basically it has, very simply, it has its brain like Jetson Text2, has the ability to run machine learning algorithms online, and has this propellers, very small form factor. So basically this 0 to 100 acceleration is basically very fast. Like for F1 racer cars, it's already like 2 point somehow seconds. And also this kind of max acceleration is more or less the same order of magnitude as you experience for a rocket launcher. And for the sensing, there is an Intel RealSense camera. It provides like depth camera. I don't know whether this one provides pulse as well, but it's not that important here. Okay, so about two tasks like the drone acrobatics and also the navigation in the wild. I think this is kind of the summary of the results. All this motions is done with only onboard sensing without any motion capture system. So you can see the drone can perform this kind of role very reliably. I think the success rate is about 80% or something. If you ever do drone experiments, it's quite high already. And also it can navigate through the environment very swiftly. So basically the key here is this is one paradigm that you do very smart training in simulation, then you can zero-shot transfer to the real world. So before we dive into the method, let's see how the data in the simulation is collected. Basically, it's max use of this kind of massive parallel simulation. Like this is, I think it's from Gazebo or Flightmare simulator from the lab built in-house. So it basically, the training process is like 6-8 hours, basically overnight. Then it has equivalently 60 days of flying on it without interruption. So with this, you can collect a lot of data very efficiently. Then you can use this data to train policy that can be finally zero transfer to the real world. So I think from technical point of view, this is kind of the gist of the work. So I will spend some time explaining this. So basically, all these to work following the same paradigm. So you have this in simulation, because you are in simulation. You have this perfect state estimation of your robot. You know perfectly where your robot is and how the environment looks like. So then if you have perfect information, the traditional method is very good. So you can have this optimal control method that give you a very good trajectory. That is if you give your full information, the best you can do. Then you have this student network, which will be deployed actually on the platform. The student network does not have this kind of pre-villaged information. It only have the information that from the onboard sensors. So then you can kind of have these imitation learning algorithms that has the students that learn from the pre-villaged expert. So it turns out works very good. Just one note that this paradigm not only works for drones. If you're familiar with the work from Michael Hooter from ETH for like full-legged dog robots, they also kind of use this kind of paradigm. It also kind of transfer pretty nicely. Apart from this expert to student transfer, there's also one key element that is not outlined in these slides. So you see that here the input is image. Actually, the input to the actual network is not image. So it's kind of data. It's kind of a abstraction of the data. What do I mean by abstraction? So basically, for the drone acrobatic work, the work fit like the feature tracks from the images to the network, and for the navigation work, they fit the depth image from the onboard RealSense sensor to the network. So the abstraction here is also very important because if you have abstraction, a very nice abstraction of your sensors, then you have I mean naturally, intuitively you will have a smaller sim to real gap. So to summarize, I think there's two key takeaways from this paradigm. Like firstly, this has this pre-villaged training. I think there's a paper called Learning by Cheating from Willard and Coulton. And also this kind of data abstraction. This is really the two key things that makes this generalizes really well. Okay, this is this to work, and yes, then let's going on for the recent part. So recent part actually it's very difficult to have this leveled expert data because, as I said, the simulation is not perfect. Then you have when you're flying really at this kind of recent high speed, you have this unmodeled aerodynamics. The really optimum control method can get you very far, but not far enough to beat human pilots. So there's some trick to mitigate the gap. Yes. So just to give a sense, like how drone racing looks like. This is kind of the Swiss champion Marvin that actually helps the lab build a drone. Like people put on goggles and have these images streamed through these goggles. So this is basically the image you'll see, like with onboard sensors. You can see the angular velocity or the speed of it very fast. Okay, so what do we do in tackling the drone racing problem? So basically, it's to put it simply, we need to find the control inputs that minimize the flight time through a theoretical gates, like here in this video. But you have a lot of constraints. You have system dynamics. You have input constraints. The rotors can only have certain thrust. You have state constraints. Like I said, the quadrotor is under-actuated. You cannot fly freely in 6-stop. Basically, it's 4-off. And you have physical constraints. And one of the tricky part, you have the perception constraints. Like I said in the previous illustration, that due to its under-actuated nature, you can easily lose track of the information you are interested than with the perception constraints. To put it simply, like if you look at human flying these drones, it always tries, when it passes through a gate, it always tries to look at the next gate. So it's kind of a human intuitively try to add these perception constraints to these internal planning algorithms. So it's a very difficult problem. Like in David's lab, first they say, okay, let's follow in the older method. What if we have a perfect perception, localization, and position of the gate? Can we just use optimum control to really plan a time optimal trajectory to see if it's feasible to beat human? So there are 2 lines of work here. I will not go into very details. Like here, it's starting from an initial trajectory. It tries to find the time optimal trajectories through optimum control. It basically has a very nice. It can reach kind of the low bound of lap time, but the optimization takes very long. Like for this fixed 1, 2, 3, 6 case, it takes like 1 hour to plan in this perfect trajectory. And if you're doing robots like perception and control in the loop, it's not possible because you always will have a non-ideal state estimation. Then you need to replanning all the time. You cannot have like I move a little bit, I replanning 1 hour, so it's not possible. But it's good reference to see how we can like achieve like what is the limit of the trajectory if we know everything perfectly. There's also another work that is from Romero, and it relaxes some constraints a little bit. It can replan very fast, but it of course you always have this trade-off. It has some inferior control performance with respect to the left part. So basically in the lab we tried to use optimum control to say that can we find some optimal time optimal trajectory. It's difficult, and also it's not working very well in practice when we put the control algorithms on board, because just as I said, all these algorithms assume perfect perception, localization, and knowledge about the gates, which is usually not the case. To give you the feeling why it's not the case, let's see the detection algorithms running on board. Like this colored thing is the gate. So when you fly through the gate, you basically use a very old conventional algorithm to estimate the position of the gate. But the thing that you have this uncertainty of the position. Like intuitively, it's like quadratic. The uncertainty of the pose of the gate is like quadratic to the distance of the gate. So this kind of thing is very difficult to model in practice. First thing, like you cannot say like I can extract the corner very reliably because you have motion blur. What is the uncertainty of your corner extraction? So it's difficult to say. And also, like I also mentioned the deformable thing. Like if you fly very fast, the drone is deformable. So this kind of thing is very difficult to model in practice. So finally, the thing that works better, it's not a full story, but works better than optimal control is to use the reinforcement learning algorithms. That also fits the, so here, the learning algorithm basically takes still the abstraction of the robot states and the world state, like position, velocity, orientation, and tries to train the policy to achieve the control method. Basically here, we need to balance a lot of cost, like the progress to the goal, like perception constraints, like whether the next gate is close to the center of the image, and also command like the smoothness of the control, and also no crash. So again, similar to previous method, this kind of makes use of large-scale parallel simulation. I think here it's like 100 drones, like collecting data in simulation. It's basically takes 1 hour, if I remember correctly. It's equivalent to kind of 1 month of flight. So with IO, with the reinforcement learning, actually gets better performance than the optimal control, but it's still not good enough to beat human. Actually, I think they tried this. It's still inferior to the human performance. So here, there's the important sim to real gap. Like here, like I think there's 2 trajectories. One is fly by in simulation. One is fly by the same policy in real world. You can see there's a discrepancy between the gap, between the 2 trajectories. So so it's like a recurrent topic. If you fly at high speed, the simulation is not good enough. So you will have this kind of discrepancy between your policy deploy in simulation and deploy in the real world. So in this way, actually, you need to do more work in modeling the effect, basically improve the simulation. So this is the aerodynamic effect I said. So the gist of this thing is that you can have a mixture model to actually model the aerodynamics. The first part is basically based on first principle, like physics, and you can model the large part of the dynamics at low speed and a large part at high speed. And for the residues that is difficult to model, that can only be modeled by computational fluid dynamics, you also can use a network to approximate it. So if you're familiar with system identification, it's basically like a fancier version of system identification that has kind of a physical space model and also neural network to model this model stuff that is difficult to model. I think this is also kind of it's not very uncommon, I say, in robotics research nowadays. Like if you're familiar with literature in MBC or something, like people are doing this for like off the nominal state. It usually works better than just to use this physics space model. Okay. So with this, all this in place, like to summarize, with this large-scale simulation, privileged training, and also this modeling of this difficult model effect, like it took a lot of time in Douglas lab. But after 7 years in June, they invited world champions to do a drone racing. I think this is they have this trailer too. I don't know what it is. Yes. So it's very fast. I think you don't see much, but basically at the end, from statistically, like the drone actually reaches the champion level of the reaches the level of the human champion. Just there's one thing I need to add. So basically for this, the machines is not cheating. So you may say that the machines can see the track of the track, can know the position of the gate beforehand in simulation, but also the human are given 1 week time in advance with the same drone in the same track to train for 1 week. Then they like form head-to-head to have this kind of thing. I think this is published in Nature and Science Robotics. All the data and code is also released open source. If you're interested, you can have a look at these papers. Okay. To summarize, to achieve this kind of agility in drone racing, the first takeaway is fine-tuning from previous rollouts. This is kind of the thing I mentioned, like when you train simulation, your your model in simulation is not perfect, then you deploy in mockup to identify the residual models, like the residual of your dynamics, the residual of your perception. Then you basically use this kind of fancier version of system identification to fine-tune the policy in simulation. This sim to real to sim really helps to push the performance when the drone flies at a very high speed. And also, don't forget, like in training simulation, we still have this data abstraction and privilege training. So it's also very crucial. And also, like at least for this specific question, drone racing, I don't want to generalize too much. Like IL seems to be work better than optimal control, because in drone racing you have this many like unmodeled effects. So in IL, the one thing you can do is that you can have a very large scale domain randomization, which usually brings very robust policy, as also seen in other work. Okay, but as a robotist, we also know that if you look at the video, everything is perfect. So this is still an experiment in a controlled environment. In real world, like robustness and versatility of the robot is still very difficult. Like in this drone racing, this is also some videos that it fails very catastrophically. If you are really slightly off by like 20 centimeters, you will hit the gut, and also the system will fail. And also, I believe people also see like many catastrophic failures of the robots. So it's kind of not very easy to transfer the theoretically very good performance to really reliable commercial products. But in real world, like birds are very agile. Like this is the example David always use. Like when can we fly like very agile like birds? Because birds like they fly very robustly. They can adjust the position and the speed of their flight on the fly. And of course, they don't have very perfect 3D information about the environment, but it is possible. It means that it must be possible, like in theory. Yeah, I think I have several minutes left, so I will quickly go through the last part. So one of the limitation of the agile flight, as I said, is the sensor. So the thing that I showed before is mostly rely on vision sensors, like cameras. So the cameras operate on the drones is usually at 30 frames per second. I don't know whether now it's higher, 30 frames per second. So basically brings this kind of blind time between frames. So you have frame, then have computation. This is already some latency. Then you have a next frame. Then between this time, you know nothing. So it's kind of of course, it will be difficult if you want to say be as agile as a bird to adapt on the fly. So of course, you can use high speed cameras, but also there's this problem of the bandwidth. If you have these high speed cameras, the frame is higher, then you have like a very high bandwidth. So it's kind of the bandwidth latency trade-off. So with this, there's this kind of novel cameras. I think nowadays it's more well known than the time I did my PhD, like these event cameras. I think this graph explains this event camera very nicely. Suppose we have a dot rolling on the plat. Standard cameras will only capture images by some frame rate, so you can only have these discrete images of the dot. But event cameras, you can think of that event cameras are like pixels that is triggered individually. So if you have a pixel at some place of the image that is saturated by the intensity change, it will trigger. So it will kind of have this kind of asynchronous pixel activation, created this nice event flow in space and time. So the key here you might see like why for agile flight, David's lab is very interested in this sense because it has a very low latency. You can basically, between the frames, you can have a lot of information here. Here is an illustration of the event camera. Basically, if you at the down here, if your arm is not moving, you do not see a lot of events. But when it is moving, you see the events coming up. Yeah. So I will skip this. So basically, this kind of the two different approaches of processing the events, like event by event, or you use some generating model to estimate motion. Basically, you have some model that regarding the quantity you want to estimate, then you maximize some cost function. We call it contrast to estimate the motion of the camera or some other quantities. I think I will just show that with this sensor, what kind of thing can we do with event cameras? So because we do not do event camera just for fun, we do it because that event camera locked scenarios that is impossible for standard cameras. So this is, I think, a paper from 2021 that it won the RAS Best Paper Award that year. So it's basically, it tries to tackle the problem that for drones, if you fly with DJI or something, when the propeller failed, the drones will kind of spin at a very high speed. That is determined by the drone's dynamics. So if there's one propeller failed, and the drone will spin like this, basically intuitively the cameras looking downwards will have a lot of motion blur. But here, since the event has a very high temporal resolution, you can see that if we somehow construct the event frame and extract features from there, you can see the feature is still very sharp on the event frame. Then actually with these features, we can run like standard view inertial odometry algorithms to recover the state of the robot. Even with this, this is still very amazing to see. Even with this like very high rotating, you can still control the robot going from A to B in a safe, and not that safe, but in a relatively safe manner. Yes. And also, this is a work that is done by David Flanga that basically tries to use event to avoid obstacles. Now this kind of approach is also try to find applications in automotive, try to detect the pedestrians at high speed. I will talk about it later. So basically, this is a video demonstrating it. This is not a good shot, but later, like if you throw the ball at the robot, the robot can detect the orientation and some simple state of the ball. Then it can reflect it in this counter policy to let the robot avoid the obstacles, which is also not very possible. Also, at least it will be very tricky if you're doing it with normal cameras. And it's the same thing, and I think also like catch ball with robot dogs. Robot dogs are now very popular. This is a nice example. Like if you want to in industry inspection, I think this is kind of a part from Boeing plane, and it tried to inspect the holes here. And previously, if you try to do vision-based industrial inspection, you need to stop there, taking a good shot, and then estimate the then try to estimate the size. Now with event is like very fast because you have this very high temporal resolution. I think it's a very promising sensor, like especially now considers with this advance of learning-based algorithms. I think it's a lot of potential to unlock this low latency nature of the event cameras. I just few words about the last one. I think this is so compare with standard frames. Event cameras are fast. They have very asynchronous events, but of course we do not have. You look at these events, it's always a little bit abstract, like what is this? So, but images are very good, rich information. So I think the recent work from David's lab is trying to combine these two. I think I go through this. Basically, it tries to build a representation of the events as a graph. Then it tries to use some information from the image to propagate to the events, and basically it tries to get the rich information from the images, but still try to have this high temporal resolution nature of the camera. Yeah, I think it's also very promising direction. Yeah, I'll skip this. Yeah, I think that's all for the talk. I think David's group assisted my PhD. Many of the work was done after my PhD. So it's really amazing work. And I think David is always hiring for very talented people and looking for collaborations. Thank you. think I'm good on time. Yeah. Yes, I think a lot of things. Yeah. Yes, I think so. I agree. Because like really the very hard to model thing happens right at the limit. Like if you have a really high speed, you have this aerodynamics. As I said, like this slowing, hovering thing, it can already work nicely if you do not care so much about speed. I think bit ordinary people, I think the first part without this identification will be kind of sufficient for that. Yeah. But I haven't done experiment for this, but I think so. Yeah, yeah. Like ordinary 100 people, like, yeah. Yes, yes. Yes. Yeah. Yes. Yeah, yeah, I agree. It's a very interesting topic. It's always like the trade-off between robustness and precision is always like very true in practice. Yes, I agree. In this champion, it's trained on the same environment. It's same track. It's the same setup as human, because the human. So to answer question, as a human, they are given also 1 week at a time to train in the same track. So as an algorithm, we also train on the same track. So. Yeah, yes, yes, yes. But I think it's an interesting question, because if you're taking the champion FPV racer, if you put this guy in a completely strange track, I think it will perform somehow okay, like not completely failure. But I think for this kind of reinforcement and algorithm that is specifically training for this track, I'm not sure how well it can generalize. I think there's still some discrepancy here between human level performance. Yes.